Remember earlier in the semester when we talked about how the ancient Greeks went about trying to find the areas of shapes that were not just squares or triangles or polygons or things that are easy to find? They invented a method called the method of exhaustion. And it wasn't called that just because it was so tiring to carry out, although it did require amazing skill, attention to detail, and so much patience. I can't imagine doing geometry that much, but they did it. And so the method of exhaustion, as you'll recall, in order to find the area of the circle, I'm just going to give you one quick example. In order to find the area of the circle, the idea is simple. You take a circle and you fill it with a polygon that is almost the same size as it. See, like this hexagon. This is a six-sided polygon. Well, I didn't draw a very good one. And as you can see, the area, even of just a six-sided shape, is really, really pretty close to the area of the circle. So if you wanted to know the area of the circle, at least approximately, you could just find the area of this hexagon. And in fact, if you wanted to get a better approximation, you could make a 7 or an 8 or a 10 or a 100-sided figure. A 100-sided polygon would, imagine putting 100 dots around this circle and then making little lines to connect them all. It would be very close to looking like a circle itself. Probably when we're looking at circles on computer screens, we're actually looking at something like a 100-sided polygon. It just looks like a circle. If you look really close, you can see the pixels. Okay, so in any event, the idea is that as the number of sides increases, in fact, as the number of sides approaches infinity, the area of the inner polygon approaches the area of the circle. In fact, let's just go ahead and make this circle be the radius equals 1 of our circle. So in this case, the area of the inner polygon would approach the area of the circle, which is pi r squared, aka pi 1, the radius is 1 squared, or just pi. So this is how in ancient times, if you wanted to know what the value of pi was, it's 3 point, you know it's a little more than 3. You can just like see that almost just looking at it. 3 times the radius. You know, this is one way you could get close to it. For instance, how do you know pi is 3.1 something? It's not 3.0 something or 3.6 something. Well, you know, because in fact, Archimedes, as I mentioned at the beginning of the semester, using this method, and something like a 128-sided polygon or something. Oh gosh, I mean, it must have been such a pain. Archimedes, he proved for the first time in history that pi equals 3.14 and some change. Big deal. And Archimedes did it by tweaking the method of exhaustion and making it more efficient and more rigorous. And he ended up being able to get this kind of degree of accuracy, 2 decimal places. The ancient Greeks didn't even have a notation for decimals. So I'm just saying, like, this is a really, really big task that he accomplished. And for all of human history since, we know pi is 3.14. It's like we know it like a nursery rhyme. It's so familiar. So that's the deal with the method of exhaustion. But the method of exhaustion wasn't just about taking this inner one, because the problem is that the inside one is always too small. It's not good enough to just hug the circle from the inside. There's still an error there. And you don't know exactly how much that space that isn't part of the area of the polygon, how much that contributes to your area of the circle, right? Like looking at this, you can see like in my drawing, actually those spaces outside the polygon are kind of big. That definitely is, I'm guessing, way more than 0.14 of the area. So I'm just saying this is like it's a big problem to try to figure out. And in any event, to do it, to carry out the method of exhaustion, you need to point this out. In your book, you saw how and you'll see a lot of this in Calculus 2. You see how the idea of an integral is that it's the exact same thing. You fill the area under the curve with simpler shapes. In this case, it's not a circle, it's a function. Functions aren't allowed to loop back around on themselves. So it makes more sense to use rectangles. You fill the area up with a bunch of rectangles that kind of hug the shape, just the same way we did down here with the circle. And then those areas are really easy to compute. Rectangles, those are easy, just like polygons. Those are polygons. They're not regular polygons. They don't have all the sides the same, but they are polygons. So I'm just saying, this is super easy. Okay, so this is that, right? The only difference is that they didn't have functions in the ancient world. Functions are a modern thing. Graphs, functions, these were invented by Descartes in like the 1500s. It's a modern structure. It's a modern drawing. But the ancient Greeks would have drawn this and done it just this way. Now I want to tell you something that's really crazy. This method, the method of exhaustion, the method of integration, this method was used explicitly, exactly like drawings like this by Leibniz when he invented calculus. But it wasn't actually proved. It was never proved logically. This was very foggy for thousands of years. People didn't use these ideas because they didn't really believe that it was true. It worked, but it didn't feel true. Does it feel true that could work? Well, you're like, yeah, teach, we just took calculus the whole semester. But if you didn't take calculus, it's kind of doubtful that you could make those exactly equal. Can you exactly make a bunch of rectangles equal that curvy line in that area? No, not without calculus. So in any event, this was actually proved in like the 1860s or something, I think, by Riemann. And that's why they're called Riemann sums, even though it's the exact same idea as the method of exhaustion. And it's the exact same idea as the way that calculus was actually discovered. Riemann proved that actually using limits, this works. Limits, the idea of limits weren't invented at first. They weren't invented till like the 1800s. People were doing calculus for hundreds of years, just by the seat of their pants, literally. And other people, really smart, legit people, were criticizing them for it and saying they were wrong for using calculus. Okay. So all of that being said, what's the idea with the method of exhaustion? I claim the method of exhaustion contains everything that there is about calculus in its idea. Because to make the method of exhaustion, well, one thing you have to do is you have to make this inner polygon. And that's just a matter of splitting the circle up into equal parts. I think you can do that in geometry terms. And then connecting the dots with a straight edge, right? You just connect the dots and you got a polygon. That's easy to do. That's really easy in geometry. The other thing you have to do to construct is you have to construct an outer polygon. You want to be able to know, if you know that this is too little, you need to also know what is too much. And to do that, look what I'm doing here. I'm trying to make a polygon, but I'm not looking at drawing a whole shape. I'm just at every point drawing a line that is tangent to the curve. So in order to draw the outer polygon, you have to find tangent lines. And that's really hard. That's hard. In geometry, I don't think it's super hard. I think it's something like make a line from there to there and find a line that's at a right angle to it. But more generally in math, as you've seen, finding tangent lines is not a trivial question. It's incredibly hard, and the only real solution to it is derivatives. That is the solution. Without that, there isn't a way to do it, except for just to do it with geometry. And so the problem of finding, so the method of exhaustion, to me, this is the storyline of the whole semester. The storyline of the whole semester starts with ancient Greece. It starts with the method of exhaustion, because the method of exhaustion says that from the start, in order to compute areas, right? The area of the circle, for instance, that's what you're trying to compute. Being able to compute the area is completely tied to the problem of also being able to construct tangent lines to the circle in order to draw that outer polygon. Areas and tangent lines from the very start, from the very first method of calculus that was ever used thousands of years ago, I claim that the problems of areas and tangent lines were interconnected. They're interconnected, going back to the mists, in the mists of time. And the fundamental theorem of calculus says the same thing. The fundamental theorem of calculus says that this feeling, this intuitive thing I just did, is actually pretty true. The fundamental theorem of calculus. In general, I'm not going to, wait, calculus. I'm going to give it in the next board. The fundamental theorem of calculus, it says that integrals areas and derivatives, which give the slopes of tangent lines, are intimately connected. They are the same. They're two sides of the same exact problem. You can find the area by drawing a bunch of tangent lines around the circle that hug it. You can find the, and you can move between it just the same way, between integrals and derivatives. Now, integrals, these aren't areas. Integrals are symbols. It's that big squiggly S symbol. Integrals aren't areas. Integrals are areas if they're definite integrals. That's what those symbols mean. And integrals are antiderivatives, which are other functions, not areas. Areas are numbers. Integrals, indefinite integrals with no endpoints, are functions. They're antiderivatives. On the other hand, derivatives, these aren't tangent lines. They're not the slopes of tangent lines. They're functions. But if you evaluate them at a particular x value, it does give you the slope of the tangent line at that value. So to find areas, that is to take integrals and evaluate definite versions of them with endpoints, to take tangent lines and find their slopes, which means finding derivatives and computing the derivative at a particular point, these problems are interconnected. They're beyond interconnected. They are as much the same thing as saying 3 is the square root of 9 versus 9 equals 3 squared. Those are the same statement, just the same way. Integrals and derivatives, they're essentially the same statement, except for you have this business of plus c on the integral side. That's the one thing to always remember, is you have that plus c business. But that is all because derivatives make the plus c vanish. It's all connected. Okay. And so now the fundamental theorem of calculus actually isn't one theorem. It's two theorems, and the two theorems go two different ways. The fundamental theorem of calculus part 1 tells us what happens when you, it talks about areas. The fundamental theorem of calculus part 2 talks about derivatives. Each of them tells you what happens when you do that thing to the other one. What happens when you differentiate an integral? What happens when you evaluate an area? How does that relate to the antiderivatives? So the derivatives and the areas are connected. Hold on just a moment. And so, excuse me for just half a second. What I want to do, I want to give you an idea of just the idea of, I want to give you an idea of why the idea of the fundamental theorem of calculus makes sense. And also in that, we're going to see right away kind of like what it means. Now, the fundamental theorem of calculus part 1, we're going to hold off on first, even though it comes first, because it's a little harder to understand. The fundamental theorem of calculus part 1 tells us what happens when you differentiate an integral. It's a little complicated. It's actually the easiest. It's much easier, but we're going to do it second. What I want to look at first is the fundamental theorem of calculus part 2, because this connects directly to our study of antiderivatives that we're in right now. So the fundamental theorem of calculus part 2, this is the one that's about antiderivatives. I'm just saying, okay? Part 1 does not deal with antiderivatives. Part 1 is almost so easy, it's that you don't even believe that it's true. The fundamental theorem of calculus part 2 is about derivatives. Antiderivatives, sorry, it's about antiderivatives. Okay, I put FTC because that's standard. Like we all call it FTC in math. Remember, the T stands for theorem. And what is a theorem? It's a truth with a capital T. It is truth, like in the highest sense, like poetry and religion are truth to you. It's truth in the sense of that when I see the word theorem, I hear angels singing in the background. Those are birds and a helicopter, but still, I'm pretty sure those are angels. All right, so the fundamental theorem of calculus part 2 is about antiderivatives. The fundamental theorem of calculus part 2 is the thing that allows us to compute areas for all shapes. Oh, I keep saying derivatives, but I mean antiderivatives. This is about areas and antiderivatives. Can't fit antiderivatives there, but the fundamental theorem of calculus part 2 is so amazing. Now recall that you know for a function, you know that this symbol means the antiderivative, plus c. You know that this indefinite integral means the antiderivative plus c, okay? On the other hand, you know that if you put a number down here, let's say a, and a number up here, let's say b, that this symbol now instead represents the area between the curve and the x-axis, remembering that it's negative if it's below the x-axis. That gets a negative sign on that area, right? Between the points A and B on the x-axis. These are the same. The shaded area is what the symbol represents. It's not the same as the antiderivatives, remember? Antiderivative is a function. This is an area, it's a number. It's that bunch minus that bunch plus that bunch. However, the area, it turns out, is given exactly by the antiderivatives. And this is so beautiful, okay? What I'm about to show you, I'll explain to you why this is so surprising after I write it down. To evaluate this, the difference, this area, look how complicated this area is, right? Your curve is all curvy, and it gets bigger, the area, and smaller as you go along. The area is like really a complicated thing. It's not just like simple like a rectangle. It's very complicated. It's plus and minus at times. This is like a crazy thing to kind of think about, actually. The more you think about it, think about trying to find an area like that of a squiggly weird function. And what's amazing is that it turns out this area is actually given by antiderivatives. This is amazing. This is very, very amazing. You take the antiderivative, and you can forget about c. I'm going to put no plus c up here either. There's no plus c in the fundamental theorem of calculus 2. You take the antiderivative of f, big F. Remember, if this is 1 over x, then this is the natural log or whatever. You take an antiderivative of little f, and you take that function. It's a well-defined function. It is a function you know. And you plug in this endpoint, the top endpoint, the right hand, the right hand endpoint of, that's B, that's A, of the area of the interval that you're integrating over. I'm not done yet. So check this out. Now look, again, f of x has all of these values. See, it's getting bigger there, it's getting smaller there. It's a curve, f of x. It's negative down here. F of x has all these values, okay? So instead, and the area involves all of those values. That's what the integral sign means. We're integrating, we're bringing together all of these different little values of the function. In any event, what this turns into, though, is insane. All of those values, all of those little areas and those values of the function and the negative and the positive, all of that stuff, it doesn't matter at all. It's gone. We don't have to think about it. You take the antiderivative of f, an antiderivative, and you just plug in the endpoint there's value, and you subtract it from this endpoint and its value. Remember, this interval, the length of the interval is b minus a, and the area sitting on top of that interval is just big F of b minus big F of a. Come on, that is like so cool. You know how to compute the antiderivative from calculus. You know all those rules in reverse. All you have to do is find the antiderivative and then only plug in the endpoints and forget about all those other points in between. And it's just as simple a calculation to find that crazy looking area as it is to just find the length of the interval itself. That, my friends, is crazy, and it's true. And it's one of the greatest facts in all of math. Areas, any area that can be described by a function where you can find the antiderivative because you know calculus, you can like have an easy formula for that area, just as easy as base times height, just as easy as pi r squared. Your formula is big F of B minus big F of A. It's so beautiful. This is amazing. Again, I've got to drive this home. You're not calculating anything at all of those points between A and B. You just plug in those endpoints. It's so easy. So here, let's do an example. Let's do the example of, because I love this example because I love logarithms. They're my favorite functions. Okay, so we're going to do the example of the area. Now, I'm going to remind you what this means in a second. We're going to look at this antiderivative. Remember that this antiderivative, for one thing, what does it mean that there's dx upstairs? That just means this. In calculus, if there's a 1 upstairs in a function, we just go ahead and treat it like fraction rules just to save space. That's all that means. So it's really the function 1 over x dx is what we're integrating.